Okay, hello everyone, and welcome back. Today we're going to look at linear programming. Okay, we've looked at systems of linear inequalities, where you shade each part, and you look at the overlapping shaded part as the solution. And linear programming uses that, but it takes it a step further. Okay, today's objective: to understand and apply linear programming concepts. Guys, the essential question: what is linear programming, and how do we use it? Guys, linear programming is a mathematical modeling technique. A linear function is maximized or minimized when subjected to various constraints. It's about constraints, okay? Guys, this technique, it's been useful for guiding, making decisions in business, in engineering. I used to use it a lot, again, because in particular, industrial engineering. All right, the social sciences, the physical sciences, linear programming is used quite a bit. All right, there are 3 classes at the University of Minnesota: linear programming 1, 2, and 3, that you can take on the East Bank, in the Institute of Technology, in the program called an IEOR, Industrial Engineering and Operations Research. Now, a typical example would be taking the limitations of material and labor. That's capacity. How much capacity do you have? Capacity has limits. You only have so much machinery. You only have so many people who can do it. All right, then determining the best production levels to maximize profits or to reduce expenses, to minimize expenses. Now, these are the steps, and we'll go through them here. And guys, I'll be honest with you, these examples that we go through, you're not going to understand them right away. All right, but we will go through it in class again and again, and you'll be okay the next few days. First thing you do is define the variables, X and Y, what are they? And define the inequalities, and then you find what's called the objective function. Are you trying to maximize? Basically, it's either profits or expenses. Minimize expenses. All right, you graph the systems of inequalities and identify the bounded area. All right, and the bounded area has vertex points, the corner points. Identify those corner points. Because you take each of those corner points and plug them into the objective function. And the objective function is an equation of X and Y. We're looking for some answer. And then once you calculate that, one of those will be the optimal point. One of those will be the maximum profit or the minimum expense, depending on what you're trying, what your objective is. As an example, this is a company that makes baseball bats, 2 different kinds, the homer hitter and the big timber. Or it takes 8 hours to trim, to turn on the lathe the homer hitter, and 2 hours to finish. And the homer hitter makes $17 profit for each one they sell. The big timber, though, takes a little longer, 5 hours to trim and 5 hours to finish. All right, but it has a profit of $29. All right, we only have so much capacity available. The time for available trimming and lathing is 80 hours. All right, the time available for the finishing is 50 hours. All right, so we set it up. I'm going to jump back and forth. This might be a lot here, guys. It's okay. You're not going to get all this right away. You define your variables. That's the homer hitter and the big timber, the 2 different bats. And what this is how long it takes to make each one. All right. Our objective, we're trying to maximize profit. Our profit was $17 on the homer hitter plus $29 on the big timber. We want to maximize that thing. All right, we set up the constraints. The 8 and the 2 had to do with on the lathe. Yeah, trim and turn on the lathe. All right, 2 hours, and then 2 hours to finish. Yep. The finishing then is right here, the 2 and the 5. There's only so much. We got 50 hours and 80 hours. That was what they said our constraints was. And again, we'll be able to set those up. I don't want to jump back and forth here too much. Again, it takes 5 hours to trim and 5 hours to finish for the big timber. So right there, 5 and 5, those two Y's right there. Whereas the homer hitter was 8 and 2. All right? This is how much hours we had available for each operation. Or what we do then is take our systems of inequalities right here, these two, and graph them. All right, we get a bounded area in the yellow here, and we look at 1, 2, 3, 4 different vertices, 4 different corners to that bounded region. We take those points, they're listed right here. All right, the X and the Y. We plug each of those into the objective function, X, Y, and calculate what the profit would be for each corner. We find that 317 is the max. That's 5 and 8. All right, so 5 homer hitters, 5x, and 8 big timbers. Because a big timber is Y. That is our maximum profit that we can make, giving the capacity constraints with our two products, $317. All right, one more example, guys, okay? I know this is a little bit hard, but we'll work on it in class. This is an electronics company. They make consoles and widescreens. All right, the equipment in the factory allows for manufacturing at most 450 consoles and 200 widescreens in a month. The chart below shows the cost and the profit of each one right here, okay? So again, first we define our variables, the console and the widescreen. We set up our objective function, how much we make on each one. We're trying to maximize our profit. We look at the constraints. So this guy got cut off here. We look at the constraints for each one. All right, this is again solving for Y is what they're doing here, just so you can graph it. That's what's going on right here, solving for Y. We see our bounded area. It has 1, 2, 3, 4, 5 corner points, 5 vertices. You plug each corner point into the objective function, which is right here. Find what our profit is. We see that again, 300, 200 is right there. All right, 300 consoles and 200 widescreens. That's going to maximize our profit. Okay, just as a quick summary. Again, the solution to the system of inequalities is some bounded region of points. And we use linear programming to optimize some objective function. All right, these, it occurs at the points, at the intersection of the constraints. It occurs somewhere there. All right, the optimization point, again, occurs at the vertices of the bounded region. You just don't know which one. So you try them all. All right, guys, the homework check, you can do it. We'll look at it in class. Our warm-up assignment is going to ask to place those steps in order. Okay? And we will go through some examples. We'll do it in class so that you start to understand a little bit better. All right, that's it. Thanks.